Folks, just a little bit more information here on these last two problems. Excuse me, on the week two homework. Uh, in this particular, the baseball problem here, where we're looking at confidence intervals for pop or for attendance. I'm going to do the first one here and make sure that it's clear on how the construct is put together, and then you can do the second. Just as a reminder here, the confidence interval, the construct is always going to be the point estimate plus or minus the margin of error, whether that's a sample mean or using a proportion. That is always going to be the construct. The only thing that changes here is the point estimate in this case is going to be a sample mean versus a sample proportion. And there's a bit of a difference on how we compute the margin of error. But I'm going to do this first set of data here. So the first thing I need to start with is the point estimate, which is going to be the mean. So equals the average let's see, 58 to 67. So just under 1.5 million. The sample standard deviation, standard D dot S of that same set of data, 58 to 67. Then I'm going to compute the standard deviation divided by the square root of the sample size. I know I have 10 data points. So there's the sample standard deviation divided by the square root of the sample size. And then I'm ready to compute the upper and lower bound with the understanding here. I think I showed you this in the video. This is a t-distribution problem because a couple reasons. Small sample, number one. Number two, we do not know the population standard deviation. So that means we're going to use the t-distribution versus the z-distribution. The inputs here, remember, because you're looking for a 95% confidence interval, that means the upper and lower bound will separate the bottom 2.5% from the remaining 97.5%. And then on the upper bound, you're basically separating that lower 97.5% from the upper 2.5%. So essentially, we're cutting out the ends of the distribution that gives us the middle 95% of the distribution, which encompasses the confidence interval. So the lower bound here is going to be equals, in this case, it's going to be the mean minus, I'm just going to use 2.26 here, 2.26 times the sample standard deviation divided by the square root of the sample size. And so the lower bound is going to be about 1.378 million. And then the upper bound is going to be the average plus 2.26 times sample standard deviation divided by the square root of the sample size. So about 1.62 million. So those, when I reinforce this idea of the construct and the upper and lower bounds, this is the work that I'm looking for. So as you go and you do the last piece of this, the only thing that you're going to have to do is you have to come up with a different t-value, and then you'll have to recompute the mean, sample standard deviation, and then standard deviation divided by the square root of the sample size. The only, let's see, what are we going to change? I think there's 11 data points remaining. Let's see, 68 to 78, that should be 11. So in this case, it's going to be same syntax, except you're not going to have 9 degrees of freedom. You're going to have 10, which should make your t-value just a bit smaller. Let's see. I don't want that. Sorry about that. That's not going to help us. Yeah, so that's going to be just a little bit narrower because you have a larger number of standard deviations. So that should get you going to finish up the confidence interval problem. Then over here on the hypothesis test problem, remember the idea is the management is looking for the proportion of or they want the percentage of non-conforming rooms to be less than or equal to 2%. So setting up the hypotheses, we're going to assume that this population parameter pi is greater than or equal to 2. That's what we're going to assume, that right now the percentage of conforming rooms is at least 2%. And then we're going to test to see if this data shows that the percentage is less than 0.02. So this is a one-tail left test. If you think of a standard normal distribution, we're looking for a very, very uncommon value in the lower part of the left tail. So that's what's given us this one tail left test. Significance level 0.05. So that's the value we'll be comparing our p-value to. So looking at, as I mentioned here, as I mentioned, equation 7.3, in my textbook, in the hard copy, it's on page 257. So what I'm going to do is just go through the computation of that. So if you look at the numerator, let's see, what we're looking for is p hat. So p hat, again, is just going to be, in this case, it's going to be the percentage of non-conforming rooms. So what I did is I took, let's say I took the average, I took the sum of all the non-conforming rooms and I divided it by the sample size 2,500. So 55 divided by 2,500 is this p hat value of 0.022. Then what we're going to do in the numerator is we take that and we subtract from it the assumed population parameter, in this case 0.02. So if I go here to this z calculation that you see in equation 7.3 on page 257, let me, I don't know that it's going to do any good if I blow this up, but let me just show you what is up here in this window. So I have M9, which again is p hat minus the assumed proportion, which is 0.02. And that corresponds exactly to what you see in the numerator of equation 7.3 on page 257. Then if you go down here in the denominator, so right here, I'll just highlight that, right there, actually right there is the division. And then you see to the right of that, I have the square root of pi naught times 1 minus pi naught over n. And so that's going to be the square root of 0.02 times 1 minus 0.02 divided by 2,500. And just make sure that everything to the right of the square root here, I have all of that, the numerator and the denominator in a set of parentheses so that Excel knows to take the square root of that entire quotient. I'm sorry, it is a quotient actually divided by n. So make sure that you have all of that in a set of parentheses. And so when I hit this is telling me that my test statistic, and remember when you're using a proportion, this is always going to be a z statistic or a z stat because you're using the standard normal distribution to find your p-value. So at this point, we know that, again, the test statistic is 0.71. Then to find the p-value for a test statistic of 0.71, the Excel syntax is equals norm, that's for the normal distribution, so norm.dist. And then the inputs that they are going to ask for is, number one, the raw data value, or to the number of standard deviations of the raw data value, I should say, which is M11. Actually, let me do this one more time just to make sure everybody's clear here. So equals norm.dist. And then you can see right under that, once you open the parenthesis, it's going to tell you what inputs are required to return a value here. So in this case, again, you want the number of standard deviations of the test statistic. And I'm just going to click on that cell, M11. And then the mean, remember the mean in the standard normal distribution is 0. The standard deviation is 1. And then cumulative is a true or false. It's asking you, do you want the cumulative area of the distribution from the far left up to 0.71? And we do, because that's what gives us the p-value. And so in this case, the p-value is quite large, about 0.76. So when I compare that to alpha, since p is far larger than the alpha value, the conclusion here, based on the null hypothesis that the mean is at least 2%, again, because the p-value is greater than alpha, the conclusion here will be that we will, let me just put it here so see everybody sees this. I'll put it in some funky color here. So we are going to fail to reject H naught. And that's all you need to say. You're going to fail to reject H naught, and that's simply, again, based on the comparison of the p-value to alpha. And since the p-value is greater you know that you're going to reject the null hypothesis. I was not going to say this when I was doing this calculation, but let me just go here and give you a quick punchline. Because, and I stressed the point up front that this is a one-tail left test based on the way the hypotheses are established. In that case, when you see a p hat value or a sample proportion that is positive, you know right away that you are going to reject the null hypothesis, because what that's telling you is that the sample proportion is greater than the assumed proportion, and there is no way that you're going to get a p-value anything less than 0.5, which obviously is not going to be less than alpha. So just a little bit more there. If you were looking for a final hint on this, I hope this is helpful. Please, if there are any more questions, send me an email. I'll be happy to help you out. Take care and have a great week.